Today I'll show you what arithmetic trees are and explain how to use them. Trees are a concept I've talked about before, and arithmetic is another area where they can be used. Why should you learn about trees? They're useful for lots of things. There are grammar trees, math trees, programming trees, outlining, debate trees, and you can use them to organize your thoughts or do mind mapping. Who should learn about trees? If you want to be a great philosopher or critical thinker, if you want to do debates, if you're curious or interested, they seem fun, or they're useful for a profession or hobby you have, then trees can help you. Learning multiple types of trees helps you understand all types of trees better. Now let's jump into some examples. Each of these mathematical expressions can be translated into an equivalent tree. Here we see something neat about trees. Instead of having 3 plus operators, we only need 1 because we can have more than 2 children for a plus operator. Here we don't need parentheses when we make the tree. This tree also shows nesting. There are 2 things being added, the 2 and this entire group. Trees also don't care about order of operations. Each thing in a tree is called a node. So this is a node, this is a node, this is a node. Not the lines. The numbers and the operators are nodes. The lines indicate relationships. The thing on top is the parent, and the things below are the children. The node with no parent is called the root node. It's the top and start of the tree. Here's our root. A node with no children is called a leaf node or a terminal node. All of the numbers are leaf nodes, and all of the operators are not leaf nodes. An operator has to have children to operate on, unless you get into special cases. I'll show you how to do the math later. First, let's look quickly at ways you can show the answer. You can have an equals node, which connects some group to what it's equal to. Here we're connecting the plus group to the 2. Here I've written the answer above the tree. You could also write it below the tree. Here I have answers next to each operator. This way you can write subtotals and keep track of what you're doing step by step. Here there are multiple equals nodes. You can do subtotals this way too. This is a bit of a hassle. I wouldn't recommend it in general, but it's worth understanding the concept. So this equals node here is saying that the 2 plus 4 is equal to 6, and I'm also reusing it to be a 6 in the tree. So we have 6 minus 1 equals 5. You can also mark the numbers you're writing with a circle, parentheses, underline, or whatever else. That's particularly useful when you don't have multiple colors. Right, now let's explain what we've just seen more. Any math can be written as a tree. It's not a compromise. It's not an abbreviation or shortcut. It doesn't have any limitations. All math can be done as a tree. It works perfectly. It is a complete system for all math. For arithmetic trees, there is a simple way to solve them. Always works. First, find an operator that only has numbers as its children, so none of its children are another operator. Basically, look for the ones near the bottom. Calculate the value for the operator, and then replace it, along with all its children, with the value you calculated. And repeat until you're done. If you're doing algebra, it can get more complicated, but for arithmetic, the method is very simple. What are the advantages of trees? They're elegantly related to prefix and postfix notation, which I'm not going to explain in this video. They show grouping clearly as subtrees. They don't need order of operations rules, arity rules, or parentheses. Arity is the number of arguments that a function or operator takes. Arguments are also called inputs or operands. So when a plus can take 3 or more numbers, that is a different amount of arity. Trees allow that, whereas regular infix math does not. Each plus takes exactly 2 things that it adds together. So you get additional flexibility for some operators. Trees also work for other things besides math, like grammar, debate, outlining. What are the disadvantages? Translating between a tree and infix math can take work. Trees take extra writing because you draw lines in between nodes. Trees are less compact. They take up more space on your paper or your screen. Trees are not on your math test. They'd probably confuse your teacher. Trees are in less widespread use. If you read a book, it'll probably have infix math in it, if it has math. Alright, let's look at how we solve some math using trees. Here are the steps. First problem. What do? We look for an operator that only has numbers for its children. So this first plus here has a 3 as a child and a plus as a child, so that's not going to work. We can't start there. The second plus has numbers for both of its children, so we can start here. And we replace with the value we calculate. So 1 plus 2 is 3. So the entire subtree is replaced. Like the 1 and 2 don't matter anymore. We could cross them out, we could erase them. We can just ignore them at this point. Now, what our tree looks like is 3 plus and 3. So we have 2 different numbers with an operator. This operator only has numbers for its children. So we can add. Another example. This one looks way more complicated and way harder, but it's not actually hard. You follow the method and you get to the solution step by step. Every single individual step is very easy. So we're going to look at the bottom to find operators that only have numbers for their children. So here's one, and here's one. These are the only 2 places we can start. So we'll do both of these. 2 plus 2 is 4, and 4 divided by 2 is 2. What can we do next? We can work our way up now. Now that this is no longer an operator, we can do this plus. It is 4 plus 1. That's going to be 5. Now we can do the 5 and the 4 together. We add them and get 9. However, we can't keep going along this branch of the tree. This minus here has children of 9 and multiplication. So we need to go further down the right side and do more subtotals. So we'll multiply the 2 and the 3, get 6. Now we can subtract. 9 minus 6 is 3. And now we can do this addition up near the top. 1 plus 3 is 4. And finally, we can do the last node. 4 times 2 is 8. So it looked like a complicated tree, but each step was simple. Doing math this way, in some ways, is actually easier than what you're used to. Now you can practice. Pause here and try doing these trees yourself. You can use a piece of paper, or you can take a screenshot and put it in some sort of graphics program where you can draw in it. I'm going to show the solutions in 3, 2, 1. If you got them wrong, double check your work. If you can't figure out what the issue is, you could post on my forum. What are our conclusions? What's the point of all this? Arithmetic trees have conceptual overlap with other trees. The concepts like nodes, parents, and children, and groups and subtrees are reused between arithmetic trees, grammar trees, debate trees, and any other type of tree. The same concept can be used many times for different things. So learning arithmetic trees should be very easy if you already understand the tree concept. If you do not understand the tree concept, it can help you with it. If you do understand it, it gives you another way to look at it. Trees are good for showing relationships between things. They show parent-child relationships, which you can also view as whole-part relationships. They show grouping well, and they show multiple levels, which are also called layers. And they show nesting, which is groups within groups. You can have a subtree with subtrees in it, with subtrees in those, and so on and so forth. And when you try to use a linear representation of that, it can get very confusing and difficult to read. You can end up with a lot of parentheses needed to show the groups. But a tree can just display it visually in a clear way. If you liked this, you can find my articles at criticalfallibilism.com, including an article about trees, which is in the YouTube description. So like, subscribe, and ring the bell.